Okay, guys, today we are going to start on our next unit. So the next thing we're going to talk about are radical functions. Okay, radical functions. That basically means functions where we're taking some kind of root. A square root or a cube root is what we're going to focus on primarily, but really any type of root we could look at with radical functions. So I want to start with a little refresher of what we saw last semester with our polynomial functions when we looked at graphs, and specifically when we talked about the parent graphs and transformations that we could see. So for page 1, I'm on the very front page of our new unit notes. For page 1, I've got 4 functions here and 6 different graphs. And what we want to do is use those properties of transformations of functions to be able to match these equations to their graphs and then write functions for the remaining graphs. So the first thing I notice is I have a couple functions that are x squared functions, quadratic functions, and a few functions that are x cubed functions, so cubic functions. So right off the bat, I can make some eliminations based on whether or not a graph is a quadratic graph, an x squared graph, or a cubic graph, an x cubed graph. So my first function is an x squared function. That means it has to be a parabola, an x squared graph. Now I see that I've got a 2 in front of my x squared. That means that my parent graph will not be shifted left or right because I haven't made any changes to x or the end of my function, but it is going to be stretched, taller by a factor of 2. So if I look at the parabola graphs that I have, one from the vertex to that next point forward isn't stretched at all. Neither is this graph, but they are shifted. Their vertex is moved off the origin for each of these. Now, if I look at graph 5, my vertex is still on the origin, but to get to my next point, instead of going up 1 and over 1, I go up 2 and over 1. So that tells me that this is the graph for A. B is an x cubed function, and since I'm subtracting 1 directly from x, that means that this graph is going to be shifted to the right 1 unit. So for an x cubed graph, I would expect the sort of center of my graph, we want to call that the kind of center point, to be right at the origin. And then to get my next nice point forward, I would go up 1 and over 1, and then I would have a next nice point going the opposite direction, going down 1 and back 1. This graph, I would expect that center point to be shifted to the right 1 unit, but I wouldn't expect to see any change in my stretch, how I get to those other points. So I know that B does not match graph 3 because that center point is still at the origin. If I hop down to 6, that center point is still at the origin, but instead of going up 1 and over 1 to that next point, I'm going down 1 and over 1. So that's not right either. This has to be graph 4 because my center point has shifted from the origin right 1 spot, and to get to that next point, I'm still up 1 and over 1. So this matches function B. C is another x cubed function. This time, we're not shifting left or right or up or down at all. Instead, we're compressing. Instead of stretching to be taller like we did with A, instead, we're going to flatten out since our lead coefficient is less than 1. So our last 2 cubic graphs are 3 and 6. We're still at the origin for that center point for both of these. But if I look at 3, I'm not going up 1 and over 1 to get to that next point. Instead, I only make it halfway up, right? I don't make it all the way to 1, I only make it halfway. I've sort of flattened this graph down. So this would be the graph of C. And then the last equation that we have is another quadratic, since it's an x squared function. The -1 here in parentheses with x is going to tell me to move to the right 1 unit. And then the +1 at the end is going to tell me to move up 1 unit. So I'm looking for a parabola that's not stretched or compressed at all, but its vertex, that center of my parabola, is going to be moved to the right 1 and up 1. So my parabola graphs that I have left are 1 and 2. And if I look, the vertex of graph number 1 is moved up 1 and to the right 1. So this matches with equation D. Now for my remaining 2 graphs, I want to write a function that matches those. So for number 2, I've moved my vertex up 1. I haven't moved it left or right at all. And I haven't stretched it at all because to get to my next nice point, I'm still up 1 and over 1. So that means that this would be x squared plus 1. Lead coefficient would stay as 1 because I haven't stretched or compressed. Nothing in parentheses with x because I didn't move left or right any. Just plus 1 at the end since we shifted up 1 unit. Then for my last graph here, number 6, I know this is going to be an x cubed graph just based on the shape. It's not a parabola, it's a cubic graph. And then I know that that center point hasn't moved at all. It's still at the origin, so I'm not shifting up or down or left or right at all. What I have done though is change that sort of stretch of my graph. And I've changed it because instead of going up 1 and over 1, I'm now going down 1 and forward 1. So what I've essentially done is taken the graph that used to look like this and flipped it. To flip my graph, I need a negative leading coefficient. So this would be negative x cubed for my function there. Now, all of these transformations you saw in Algebra 1 and we saw last semester, we're going to fall back on these. We're going to rely on these as we start to graph our radical functions. So on the next page, the first thing I want to look at for graphing my radical functions is what do the parent graphs look like? That's how I determined which functions matched each of those graphs for page 1. I knew what the parent graph should look like, so I looked for any of those transformations. So we're going to start with looking at the parent graphs for the square root of x and the cube root of x. Okay, so we've got a couple of values here to plug in for x, and we'll see what we get for y. Remember, if you get stuck graphing a function, you can always make a table. That's always an option. If you get stuck, make a table. So that's what we're going to start with here. So if I plug in -4, I want to know what's the square root of -4. Well, from last semester, we know if I take the square root of a negative number, that's going to give me something imaginary. So this would actually be 2i. That's a problem here because I don't have imaginary numbers. While I know that the y value would be 2i, I don't have imaginary numbers on my coordinate plane. So this is not something I'm going to be able to graph. I see a similar problem when I try to plug in -1. So I know the square root of -1 would just be 1i, or just plain old I. So I can evaluate that and get a y value. But when I go to graph, I can't graph imaginary numbers on the real Cartesian coordinate plane. So I'm not going to get an ordered pair for either of these. When I plug in 0, square root of 0 is 0. So now that I have a real value for y, I have a point that I can plot. Same with 1, the square root of 1 would be 1. So I would have the point 1, 1. The square root of 4 gives me 2. So I would have the point 4, 2. And then our last value here that we're going to plug in for x is 9. The square root of 9 is 3. So I would have the point 9, 3 in my graph. Now I want you to notice that we've only plugged in values for x that would have a nice square root. We could plug in anything that we wanted here. We could take the square root of 2 or 3 or 5, 6, 7, 8, but they're not going to have nice y values. For our parent graph, we're just going to try and look at nice points, not points that are going to have decimals. So now I'm going to go ahead and plot these. So I have the point 0, 0. I have the point 1, 1, and then 2, 3, 4, 2, and then 5, 6, 7, 8, 9 would be here, 3, just off my graph. And I get a graph that looks like this. Now our square root graph is a little unique from anything that we've seen so far because we have a terminal point here. I'm not going to be able to plot any points past an x value of 0 for my parent graph because any negative values that I plug in, even -1/2, -0.00000001, they're all going to give me imaginary values for y. So I have this sort of end point here, this terminal point to my square root graph. Okay, so I'm going to call that our key point. that sort of end point for our square root graph is at 0, 0 for our parent graph. And then I also want to keep an eye on where that next point is, because that will help us determine anytime we have a stretch or a compression of our graph, I need to know where that key point's going to go, and then where will that next point go. So our next point is at 1, 1. So for the parent graph, my key point is at the origin, and that next point on my graph would be at 1, 1. Our domain here is going to be restricted because if I plug in anything negative, I'll get imaginary y values, which I can't plot. So our domain is going to have to be greater than 0. So we can actually include 0 in this because 0 is okay. So 0 up to infinity. Since infinity is not an actual number, I use a parenthesis there. And then our range is also limited because, again, of that terminal point. So the lowest y value I'll have is 0. Since I actually have a point there, I get a little bracket. And then anything bigger is okay. My square root graphs grow pretty slowly. That's okay. Eventually, I'll get really big y values if I plug in large enough values of x. So that's our square root graph. Now let's take a look at our cube root graph. So again, I want you to notice that the values for x we've chosen here are things that would have nice cube roots. I could plug in 5 to this cube root function. I'm just not going to get a very nice y value. And for our parent graph, I would like nice points to be able to talk about. So let's go ahead and plug in the values that we have here. So the first thing I'm going to look at is the cube root of -8. Okay? Now, cube root's a little bit different. That means something multiplied by itself 3 times gave me this number. Since we're multiplying 3 times, move my cursor out of the way. Since we're multiplying 3 times, that means I actually could have a real value solution when I take the cube root of a negative number. And in fact, -2 times -2 times -2 would give me -8. So my solution here, if I evaluate what's the cube root of -8, would be -2. So with that negative value for x, I get a real value for y. The same with the cube root of -1. I want to know what multiplied by itself 3 times gives me -1. So the cube root of -1 would be -1. So I'd have the point -1, comma, -1. For 0, the cube root of 0 would be 0. 0 multiplied by itself 3 times would give me 0. The cube root of 1 would be 1. So I'd have the point 1, comma, 1. The cube root of 8 would be 2, since 2 multiplied by itself 3 times would give me 8. So I have the point 8, comma, 2. And then for 27, that cube root would be 3. 3 cubed gives me 27. So 27, comma, 3. I'm going to go ahead and plot my points here. So when x is -8, my y value is -2. Then I have the point -1, -1, 0, 0, 1, 1, 8, comma, 2. And then our last point, 3, comma, 27 is going to be pretty far off our graph, so I'm not going to worry about that one. I'm going to connect my points here and throw my arrows on the end. And there's my parent cube root graph. So some key features of my parent cube root graph. This sort of center point here, I'm again going to refer to as our key point. And notice that it is at the origin. So that key point's at 0, 0. And then my next point is up 1 and over 1 at 1, comma, 1. So again, I'm going to refer to that as my next point. That next point is important to know because, again, it will help me determine if I've stretched or compressed my graph at all. For our cube root, our domain this time is not restricted. So our domain is anything from -infinity to positive infinity. And our range is also not limited. So our range would be anything from -infinity to positive infinity. So once we have an idea of what our parent graph should look like, we can start talking about graphs, transformations of these graphs with kind of modifications made to our functions based on those transformations that we looked at last semester, that you looked at in Algebra 1, and that we reviewed on page 1. So if you would for me, please turn the page and let's take a look at a few examples on page 3. So on page 3, we're going to take a look at the even numbered problems. We have, again, our set of functions up at the top and then our graphs down at the bottom. We've got 4 functions and 6 graphs. So just like that warm-up page, we'll have a couple of functions that we'll have to write ourselves, but that's okay. So for number 2, the first thing I want to notice is that this is a square root graph, right? It's got that terminal point. We're only going in one direction. So this has to be a square root function that I've changed somehow. So the first thing we're going to look at is how have I changed this graph? Well, that terminal point, that key point, is still at the origin. So I haven't moved it up, down, left, or right at all. The only thing that I've done is change how it grows. So my next point should be at 1, 1, but it doesn't make it there. Right? I only get halfway up. So what this tells me is that I've compressed this graph. And since I only make it, I'm estimating about halfway up, I'm going to jot down that we compressed it by a half. Now, if I look at my functions up at the top, I'm looking for a lead coefficient of a half. D has a lead coefficient of a half. It's a square root graph, and I haven't changed the function in any other way. So I think that this graph matches equation D. Now I'm going to look at the same thing for number 4. This time I've got a cube root graph. My center point, my key point, is still at the origin, so I'm not shifting it up, down, left, or right, but it does look like I've stretched this out. I would expect my next point to be at 1, 1. Instead, it's at 2, 1. So this has been stretched by 2. So I'm going to go up to my equations at the top and look to see, I know we used D already, look to see if I have any cube root functions that have been stretched by 2. That would be C, no other changes, just that lead coefficient is changed to 2. So my equation here is C. And then for number 6, same idea. I want to take a look at what type of function I have. So based on the shape, this is a cube root function. And now I want to look at how I've changed this function. So my key point is still at the origin, so I haven't translated it anywhere. What I have done, though, is change how it grows. So I would expect my next point to be at 1, 1. Instead, as I move forward 1 spot on the x, I'm moving down 1. So I've actually flipped or reflected this over the x-axis. I'm going to say I flipped this horizontally because I flipped it over a horizontal axis. So that means that I'll have a lead coefficient that's negative, just like we saw in that warm-up problem. If I go up to my 2 remaining functions, the only cube root function doesn't have a lead negative coefficient, so it's not A, so I'll need to write this one myself. So this would be y equals negative cube root of x. We're going to look at a few more example problems on page 4. So if you would for me, please turn to page 4, and we're going to look at number 1 and number 2 on page 4. Again, the same idea. We've got some graphs here. We've got some functions up at the top. So we want to do the same thing, figure out if we can match the function to its graph, or if I have to write the function myself. Again, I'm going to start by identifying the function that I have. This would be the cube root function. So I can see that my center point here is moved off the origin. We've moved to the left 1. And then if I look for my next point, it should be up 1 and over 1 from that key point, but this time it's up 2 and over 1. So I've also stretched this. So I'm looking for a function that would shift to the left 1 and stretch my graph by 2. And it must be a cube root function. Well, it's not A because that's not stretched at all. And this would move me up 3, not to the left 1. B is a square root graph. C is another cube root. I have a 2 for a lead coefficient. That would stretch me by 2. And then this plus 1 under the root with the x would move me to the left 1. So my equation here would be C. For number 2, we're looking at one more square root function. Okay. And this time, instead of that terminal point, that key point being at the origin, it's 1, 2, 3, 4, 5, 6 units up. And then my next point should be up 1 and over 1. Since it is, that tells me I haven't stretched this graph at all. I've just moved it 6 units up. So if I take a look at my square root functions, B is going to be 6 units up. So B would be my equation here. Okay, we're going to do some more practice with these when we see you guys in class. But we're just relying on those transformations of functions that we've already seen to continue our work here with graphing.